This is a revolution in the department.
Well, I guess we just copy it from Chernoff. Yeah. So to do that, to characterize the base risk, I could introduce what's called the Chernoff information, which for any two distribution f is the subpremium over what is called the Chernoff divergence. So the Chernoff T divergence, just take the density, integrate it over, take the log, and then take the subpremium over all T01. So the classic result of Chernoff is that this Chernoff information is the exponential rate at which the base error decreases as you get more and more and more data points. So as the number of data points m on the distribution f increases to infinity, and you want the distribution between these two distributions, the rate of decreases of the error is proportional, the exponential rate is given by the Chernoff information. So the larger the Chernoff information, the faster the rate of error of decrease. And it turns out that the same phenomenon holds if you extend to more than two hypotheses. Then you can just look at the minimum of the pairwise Chernoff information. And that will give you the infimum rate of decrease. Okay? So we now want to say, okay, so we're going to apply this to our embedding methods. So we return to the problem of formulating an appropriate measure for the large sample optimal error rate for recovering our block assignments. So because we can think of this clustering problem as, God forbid, a hypothesis testing problem. So given a data point, that's whether it becomes, or given m new data points, that's whether it comes from one distribution, which is one block, or from another distribution, which is another block. And if you have m blocks, you can make it like the m version of the problem we said earlier. So therefore, we will say that we will use the minimum of the pairwise Chernoff information between the block conditional multiple normal distribution that we obtained earlier from our ASC and LSA. So we have the normalized sample normal approximation, so we can compute the Chernoff information easily. So the Chernoff information for two multiple normal distribution can be written in terms of what is called as a glorified Batakaria distance, except that you have this determinant term here, and so you have to take the subpremium over T01. For some problem, for example, when the mu0, mu1 are one-dimensional, there's a closed form expression. But in general, you don't really have a closed form expression for this Chernoff information, but you can evaluate it because numerically. So since we know that we will have the large sample normal approximation, we can use this notion of Chernoff information and compare our embedding methods. So with that said, so the reason now I just want to emphasize why we consider the Chernoff information. So for any given T01, the Chernoff T divergence is just this simple, I guess, integration here. Then that the Chernoff divergence for any T is an example of an F divergence. So for example, C1/2 is the Batakaria divergence. The nice thing about F divergence is that it is invariant with respect to invertible transformations. So what that meant is that you could transform the data no matter how you did after you embed. As long as the transformation is one-to-one, you cannot increase the Chernoff information. You can increase the F divergence, or in this case, you cannot. And then furthermore, no matter which transformation you do, you will decrease the Chernoff. You will not increase the F divergence. So in a sense, the F divergence is invariant. So even after you transform, you won't get better clustering. You won't get better lower bound performance. Okay? So any F divergence such as Kugat-Libler can also be used, but we choose the Chernoff just because of the explicit relationship with the base risk. But any F divergence will be valid for comparison. So for one-dimensional space, in this case here, for one-dimensional space, the two-block model, one-dimensional space, then I can evaluate the Chernoff information exactly. So for large M, it is equal to this for the spectral embedding, and equal to this for the Laplacian spectral embedding. So for this model here, for the two block, the Chernoff information between these two blocks for the spectral embedding is this quantity, and the Chernoff information for the Laplacian spectral embedding is this quantity. And it is unclear looking from this expression here which one is larger. So I'm just going to plug it into the computer, run it along, And I get this figure here, which displays the ratio of the chain of information for various choices of P and Q in this one-dimensional but two-block model story. This is one-dimensional but two-block, a rank one but two-block model. So this is the ratio of the chain of information. If the ratio is bigger than 1, agency spectrum embedding has smaller optimal and smaller large sample optimal error rate. And if the ratio is less than 1, then Laplacian spectrum embedding has smaller large sample optimal error rate. Okay? So we see here that neither method dominates. Over here, the ratio is less than 1. Over here, the ratio is bigger than 1. You can also observe that in general, it seems like SP here. So the graph here, as the graph becomes more sparser and sparser, the ratio gets less than 1, which suggests that Laplacian spectral embedding prefers sparser graph, and ASE is better for more denser graph. And in fact, Joshua and Gary and I have a paper coming out soon that will submit it soon that will clarify this phenomenon. So this is in the two-block rank 1 model.
But isn't it even more noteworthy that these numbers, if I'm reading them correctly from back here, they only range from like 0.95 to 1.0005 or something.
Yes.
So it's like, okay, you do a little better and a little better, but
Yep.
but pretty close to the same.
Yeah,
right?
pretty close to the same. Yes.
Yeah, right.
So, I mean, that's why this is large sample. So in a sense, after a while, you see that they get almost exactly error. But maybe Joshua,
in different model regimes, you can see them vary from as low as 0.9 and up to 1.7.
Oh, okay.
So there are larger deviations in magnitude than what's shown.
Mhm.
And so I can do the same for the 3-block model, but I get the same story. So this is a 3-block rank 3 model, and I can evaluate the chain of information. And once again, I see that neither method dominates. So I think that should then. So I will skip the GDPG and just mention our discussion here. So to conclude, we present central limit theorems for the eigenvectors of the agency matrix, the normalized Laplacian matrix. These limit theorems that allow us to compare the embedding methods via chain of information. And it turns out that for large sample optimal error rate, neither methods dominates with respect to subsequent inference. So I just want to say here, the subsequent inference is that once you embed, you cannot go back to see the graph. Because if you can go back to see the graph, you could get different or even better clustering performance. This one is only working on the embedding alone. That's all you're given once you embed. And it turns out that K-means is inferior to Gaussian emission modeling because of the non-spherical symmetry. So in this talk, I present the result only for that graph where the average degree grows at order n in the number of vertices, but the results are valid even when the average degree grows at the rate of logarithmic n, something faster than logarithmic. We cannot go to constant. The average degree cannot be constant because then the agency matrix no longer concentrate. So then spectral embedding then, naive spectral embedding then does not work. You have to do some additional regularization by adding things to the diagonal and so on and so forth, which is much more complicated. So in a sense, in the barrier for which spectral embedding works, our results is valid. And so topics of further investigation includes, like I said, regularized spectral embedding for the case where the average degree is of constant order only. Here we present the case where we assume that we know the true dimension of our latent position D. But what happens if we embed if we choose D by data, so D is equal to D prime, chosen by data, so what happens if we embed into D prime less than the true dimension? It turns out you can get the same similar CFD. What happens if we embed into the larger dimension, D prime bigger than D? It turns out the problem is much more difficult, or an open question. What happens if the true embedding dimension grows with the graph? So then what happens if you embed into if the embedding dimension grows with the graph? What can you say about that? And we're working on that one. Okay? And finally, the chain of information here characterize an inference task for single graph clustering. Can we do can we have a similar measure for inference of multiple graphs? Suppose I have two graphs and I want to test whether they're from the same distribution. I could embed each of them. Each graph will be n points in RD and maybe n points in RD. I could then do, say, compare whether these 2 points clouds come from the same distribution by doing the kernel density estimate or something along the line. But can I have a measure of how well the optimal performance I could do for the current testing of 2 graphs for either ASE or LC? Is there a similar measure to the chain of information for a single graph? And that is also an open question for us. So with that said, I think these are the references. Thank you.
I have a question. It's very nice. Since you mentioned brains in the beginning, neurons, I have a question about brains. So, I mean, if you have neurons that are located nearby in the brain, aren't they more likely to have connections?
Yes.
So in some sense, you're throwing away information in order to
Yes.
make this whole technology work for you.
Exactly, and I'm guilty as charged. And so the literature has a paper, I guess by Joshua Augustine, on like what is called covariate assisted clustering, and I don't think it has been properly addressed yet. So I think that's one of the few papers I know on that topic. I think there's a lot left to be done, but we yeah.
So do you? But I have no idea what the answer is. Like how drastic is it? I mean, is it the case that do we know that nearby neurons are much more likely to be connected? Or?
And I guess my answer is I don't know either because I just put the motivation.
Well, just imagine the mess it would be.
What?
You had to just imagine the mess if you had to really draw have axons that go all over the place.
Right.
I don't know. I would assume
You mean if
that
nature had to create them? Is that what you mean, or draw them?
Yeah.
Other questions? Okay, it's time to meet again. And refreshments as usual in 301. Talk to sure, okay.
Yes.